Hello and welcome to another lecture of AI Simplified. Today we are going to talk about a very interesting architecture in artificial neural networks called recurrent neural networks. From here on we call it RNN, that's how industry knows it. So let's just start. In this class we're going to talk about what is the actual recurrent neural network, what is the use for it, and what are different types of architectures for it. When I introduce the course, I am sure you will all get confused. But once we go through one numerical example, you will have it forever. So that's why we are going to jump into a numerical example and see how recurrent neural networks work. And then we're going to talk about different use cases. So what is sequence to sequence, sequence to vector, vector to sequence, and encoder-decoder architecture. Then we're going to discuss about some issues that come from recurrent neural networks. Unfortunately, the issues are actually very serious. One of them is unstable gradient. It's very, very common for the recurrent neural networks to either have exploding gradients or vanishing gradients. We're going to discuss one way to deal with it, but honestly, because of this issue, recurrent neural networks as a standalone architecture, they're not being used that much. I know it may sound disappointing that we're covering something that is not being used that much, but these are the fundamentals for something that is being used so much, like LSTM methods or GRUs, and those are integral parts of some of the other architectures that is currently taking the world, the AI world. I want to have an acknowledgement here. I'm using this book. I think the materials that I'm covering, most of it is coming from chapter 15th of this book. It's an amazing book. I highly recommend you get it if you can and afford. So what are recurrent neural networks? Recurrent neural networks are a specific architecture of neural networks that can work with any sequence of arbitrary length. So what is a sequence of arbitrary length? Let's say you want to make a prediction about the stock price tomorrow. Some stocks have just recently been IPO'd. Some of them have been IPO'd in 1990s, some of them from, I don't know, 1950s maybe. I'm not sure if they're, yes, I think they could have been IPO'd in 1950s. So as you can see, we have a very different amount of information about each stock. The one that is IPO'd last week, we only have 6-7 days of observations, maybe 5, because if we count working day, only for working days. Whereas something that has been 50 years on the market has a lot more observations. So the great thing about recurrent neural networks is it's a structure that can work on any size. The previous examples that we used, they all have fixed size. And this one is the first architecture that we are introducing that you can use with any size. In each time step in recurrent neural networks, if we are talking about time series, we are having a model predicts two things. One is the output of that specific time, and the other one is a hidden state that it fits to itself in next round. So on the left side, you're seeing a graph that shows exactly what it does. So let's say let's say you want to make a prediction about the price of the stock that is IPO'd just a few days ago. So the input X would be the first day of observation price, and then that creates a hidden state that will be fed to the model alongside the second price, and then so on and so forth. The right-hand side is called the rolled out version of this network that just feeds it into itself. It shows that how the whole thing works. As I promised to you very early, I'm gonna explain it in a very clear numerical example, because I understand if this is the first time you're being introduced to recurrent neural networks, it can become very confusing. But bear with me, have a piece of paper with you, please. And I am going to work on a numerical example now. All right, let's look at one example by which we understand how recurrent neural networks work. In this example, what I'm going to use is, I assume we have observed quarterly prices of oil prices, and we want to decide whether or not Fed is going to increase the interest rate for us. Usually when inflation goes up, which is usually a lagging indicator, Fed is going to increase interest rates. So what we are trying to predict is whether or not Fed increases interest rates. So these y-hats is predicting whether or not Fed is going to increase interest rates. So here the average price of oil prices was 70 2 quarters ago. It was 30 a quarter ago, and 100 right now. And as you know, usually what is important is the actual change in the oil prices that increases inflation or decreases. So if it's always at 100, probably we get into a steady state. But what matters is if it was a substantial change somewhere. So one thing that is important here, let me delete this part because I don't want to confuse you. What is important here to know is in any recurrent neural network, you usually have few parameters that you need to estimate. So in this case, we only have one type of input, and that's the price of oil. And then we have hidden states that move from a state to a state. For example, we have a hidden state here. It goes to a ReLU function. It introduces another hidden state, and alongside the new price of oil, it feeds to this neuron and it introduces another hidden state. At the same time, we have y's that are probabilities that will be estimated based on the hidden estimate that was introduced, and it gives us the probability of whether or not the Fed is going to increase our interest rates or not. And the whole neural network here can be introduced by 5 parameters here. Is weight that will be added to the price, weight of the price input, then weight of the hidden state, then weight on the y, and lastly the biases. So we have a bias that feeds to this ReLU function, we call it B1, and we have another bias that would be added to y hats to make the probabilities. So here we really don't care about these 2 probabilities because they have already happened. This is like the last quarter and last quarter. We already know whether Fed has increased the interest rate or not. We already know. So what really matters is y hat 2, which is this quarter. See how it goes. But one thing to note that, again, as we mentioned, these weights of hidden states is remaining the same. We just rolled out the network, same as these. So it doesn't change from one period to another one. And that's why if I roll it even further, doesn't matter. They remain the same. The complexity of neural network will remain the same. So without further ado, let's just start calculating the next hidden state. So since the last observation that I have was 70, so very, very, very last observation is 70, 2 quarters ago. We didn't have any hidden state before. We usually start from 0. As far as I know, I do not know any use case that starts from a non-zero hidden state. So we start from always a hidden state of 0. That means we are not carrying any information from previous ones. So let's just start calculating H1 here. So H1 would be ReLU of 70 times 0.05 plus 0 times negative 0.5 plus its bias, which is -1. And that gives you 2.5. So this will be 2.5. That's the hidden state. And then y hat simply is defined as logit of 1. So here we have 1 times 2.5 plus its bias, which is -3. So that will be logit of -0.5, which, to remind you, that's exponent of -0.5 divided by 1 plus exponent of -0.5, which is going to give you 37%. So this probability is 37%. Yes, we calculated that, but not really useful. So now we are carrying some information from previous rounds, and that's the hidden state. That's gonna get into the next state. So let's start calculating H2 here. So H2 would be ReLU of negative 0.5 times 2.5 plus 0.05 times 30 plus its bias, which is negative 1. This is a negative number, and ReLU of any negative number is 0. To remind you, ReLU worked this way. So it was 0 here and then became unity here. So in order to calculate y hat 1, we just need to find the logit of 1 times 0 plus its bias, which is negative 3. So that logit would become 4.7%. I'm not going to spend time to put it in exponents because we already did it. So it's 4.7%. Again, this was the probability that Fed would increase interest rate last quarter. It has already happened. We calculated this so that to show you how it's calculated in some neural network. It's important to have these predictions. We're going to get into different architectures later. So now, lastly, we want to say, given 100, what is the probability that we are going to see Fed increasing their interest rate? So we need to introduce H3, and H3 will be simply ReLU of negative 0.5. I forgot to put 0 here. Okay, times 0 plus 100 times 0.05 plus its bias, which is negative 1. So that would add up to 4. So y hat 2 will become logit of 1 times 4 plus its bias, which is negative 3. And logit of 1 is simply 73.1%. It's very, very likely that this quarter, Fed is going to increase the interest rates. So one way to interpret this hidden essay in this specific example is how hot the economy was, or how hot the inflation data was in previous states. So as you can see, when it was 70 is a relatively large number, and that's why what went into the next state through this hidden essay was 2.5. But 30 was a very low amount for the price of barrel. So that's why something like very cold get into it. So the Fed was fine last quarter, so that's why nothing too much serious came from last quarter. But when it became 100, that contributed so much that it increased the probability to 73%. And then for next round, 4 is going to get propagated to the next one, meaning that if x2 is again high, this probability even go further away. Some learnings here, which I want you to carry with you, is that, first of all, the whole network can be estimated by just estimating these 5 parameters here. So once we learn these parameters and look at historical data, see what they have, we adjust the weights based on backpropagation, we will know the whole network. The second thing we want to know is, if we train such a network, even if you're working with data of 20 data points, still you can roll it 20 times and still you can make a prediction. That's why you have a flexibility of any level of input that you want. And that's the beauty of recurrent neural networks. That's why it used to be used in NLP a lot. Another learning here is, in this very example, we really didn't care about the predictions of these middle layers, these outputs that were before y hat 2. So we did the predictions, and we will use it to adjust the weights in backpropagation because we have already observed the probabilities here. But we really didn't care about these predictions. This was the only prediction that we cared about. So these types of networks that you only care about the very last predictions is called sequence to vector architecture. So this is an example of a sequence to vector architecture. However, there are cases that we care about the whole sequence. We want to have a sequence to sequence architecture, or you want to have a vector to sequence architecture. So there are different ways to consider recurrent neural networks. And let me summarize like 4 types of recurrent neural networks that we can have. So here we had a sequence to vector. And by the way, you're not bounded to just make predictions about one output. You could predict 10 outputs. For example, you could predict whether or not Fed is going to increase interest rate as one output, and then you may use it to make predictions about the price of oil next time. You can do all of that. So you can have multiple outputs. And you don't need to have only one input. So for simplicity and computation example, I just use one input. You can have many inputs. That's totally fine. You can just input all the pixels of a picture here. So let's go through the different architectures of recurrent neural networks. So here we introduce what sequence to vector look like. So in order to be to have a place that we have all of it at the same place. So in sequence to vector example, as you saw, you care about different x's. So you have x0, x1, x, and you continue that. So let's say you get x time t, and you only care about the y hat at time t. Okay, so you ignore all of these. So these are all ignored. Okay, you can predict them, but there's no use for it. One of the examples is you are given the whole text, and so there are a sequence of words that are coming in, and you are predicting, let's say, the sentiment of that text. Okay, so this is an example sequence to vector. You can have vector to sequence example where you only input once, or you repeat inputting the same thing, but you're generating a sequence and you care about the predictions of that. Let me give you an example. Imagine your input is a picture, and your recurrent neural network tries to generate caption for this picture. So the first output will be word 1 in the sentence. The next one would be word 2 until we get into the end of the word, which is like dot or period or question mark, exclamation mark, or anything like that. So that would be y hat of end of sentence. So here you just input the picture once, or you can input the same picture over and over again. It doesn't matter. You can do it both. So here you can assume it's everything else is 0, or just like picture is being repeated over and over again. But the thing is, you only input one vector in, but you cared about the predictions of all the words here. So you use them all. So that's called vector to sequence. You can have sequence to sequence. So this example that we said vector to sequence was an example of it that I want you to remember. Captioning, let's say, a picture. This example is like sentiment analysis of a text, but it's fed like one by one word. But sequence to sequence, not only you care about the inputs that you have here, so you input different things, but you also care about the predictions. So every single prediction you make here is important. So one example I can tell you is, let's say you're speaking over Zoom. So the inputs are voice. So it's like the first word gets in, the second word gets here, so on and so forth. And the outputs are the labels or captions, closed captioning that is being created. So you care about that. So when I say, I am, let's say, Hamed, when it's here's I, you want it to predict I, and then like am, and then so on and so forth. So that is sequence within sequence, meaning that you care about the inputs and outputs. Lastly, we can have encoder-decoder framework. In encoder-decoder framework, we have two connected cases. One is you don't care about anything in between. So you have a word to vec here. Sorry, not word to vec. Sorry for missing things. So you have a sequence to vector here. So you input things, you only output one thing that matters. And let's call it a hidden state. So you ignore all of the other predictions that is coming here, but you care about the inputs. And then once this vector gets into so that's the encoder part of the architecture. And then it passes all the information through a vector to the decoder part, but it gets fed only once based on this decoder. And so it doesn't have any input but this vector, and it decodes the output. So let's say y hat 1, y hat 2, and so on and so forth. One of the best examples I can give for this encoder-decoder one is when you have translation tasks. In translation task, you write a sentence, you decode a complete sentence. So let's say an English sentence is decoded to a vector. Then this vector is fed to a decoder to unroll it into, I wrote doctor. I don't know why I wrote doctor instead of decoder. So decoder, and it rolls out the translation into French. So it's important that you have the whole sentence being read here, because the context is important, everything else is important. And it's important that this decoding understands the whole representation of that sentence so they can make a good translation. So anyhow, so we have 4 types of recurrent neural networks. Sequence to vector, this is a numerical example that we had. And then vector to sequence, that's an example of captioning a picture. You only input once, but the outputs are important. Then we have sequence to sequence, that we have all of the input sequences are important, and also output sequences. I think voice to closed captioning is a good example of that. And lastly, we have encoder-decoder framework, where you encode everything through a sequence to vector, and then you decode everything through vector to sequence. At the end, you have a sequence to sequence, but through a vector. And that's what differentiates it from a sequence to sequence example. Another problem that we can deal with when we are dealing with recurrent neural networks is vanishing or exploding gradients. What it is, unfortunately for recurrent neural networks, we always have this issue, either of the two. Not always, but almost always. So let me roll a recurrent neural network. So if you roll a recurrent neural network, let's say this is x0, and then you have like x1 and x2, and let's say you have wx here. So ReLU is just a linear function. Imagine this is just a positive thing that is going on, and x1 and x2 and everything else is 0. And let's say this one has a wh, okay? So the first one is, and let's say h is 0. For simplicity, I'm doing it so that you can follow the whole thing. So, and imagine x0 is a positive thing, wx is a positive thing, so it generates positive things. So h1 in this case, and imagine bias is 0. So I want to make things simple so that you can follow the math. So h1 in this case would be wx times x0. In the next round, it should be multiplied by wh. So that will be, h1 will be wh, wx, x0. Because everything else was 0, and we said bias is 0. The next time it would be, h2 would be just multiplication of that by wh, so that would be wh squared wx, x0. Next time it will be wh cubed wx, x0, and so on and so forth. So as you can see, that first observation still is playing a role through like these exponents. And the problem of exponents is, imagine the wh was less than 1. So there was somewhere between 0 and 1. And imagine you have rolled it like many times, like hundreds of times. Then your h and will converge to 0, because when you put a number between 0 to 1 to the power, it becomes smaller and smaller. So you will have vanishing gradient problem. But when wh was more than 1, then h0, why did I put h0? Depending how many times you roll it, but if it's like t is like very large, it will converge to infinity. So you have exploding gradient problem. And because of that, training and tuning very large neural networks will be hard. And you have to, and you always deal with these problems there, almost always. There are techniques to deal with it. We can use our famous recurrent dropout method, where with probability p1, you ignore, let's say, x at time t, and with probability p2, you ignore hidden state t when you're doing the tuning and training and back propagation. But anyhow, this problem is a very serious problem, and unfortunately, that has limited the way we are using RNNs, it's pure form. It also suffers from another issue. Another issue that it suffers from is very short memory. And the problem is once you add more and more and more data, more and more, less and less observation from previous states would be carried forward. In the previous example that I gave you, I assume these guys are 0, but in reality, x1s, x2s, x3s are not 0 most of the time. And the further you go, it starts forgetting what has happened here. And this makes it to have a very short memory. The memory usually lasts for 10 episodes, but sometimes it's important to know what has happened before 10 episodes. And because of that, we are having a problem. And that's a very short memory. And that leads us to use some techniques to resolve it. Actually, that's our lecture next time. LSTMs and GRU is one way to deal with them. There are two different ways to long short-term memory, and GRUs are two ways to deal with this short memory. But in essence, what I'm trying to relay is recurrent neural network, despite their flexibility and their beauty and the theoretical applications that they may have, which makes it like very flexible, on their pure form, they're not being used that often because of these two issues, vanishing and exploding, gradient problem, and also very short memory. So that's something to keep in mind. Lastly, what I want to discuss is you can have deep recurrent neural networks, by which I mean, imagine you are inputting some inputs and then you have more than one layer here, okay? So you have like layers like this, goes through each other, and then they produce, let's say, y hat 0. And let's call it h, like h0. This is like h0 prime. These are the hidden states of every single one of these hidden nodes. And then when you roll it, each one of them, sorry, this is 0. Each one of them is going to pass a hidden state to the next layer. So h prime 1, h double prime, triple prime 1 to a deep neural network using x1 as input. And then you have this network to create y hat 2, y hat 1. So this will be the enter of, okay, my apologies, it looks so ugly. I take that back. So let's do this. Okay, let's be more clear. Okay, so it would look something like this, and so on and so forth. So you can have more than one input layer. In the example, a numerical example that I gave you, it was only one hidden layer there, through layer, but we can have like more than that. That's nothing theoretically and computationally precluded us from doing it. You can have, this is called deep RNNs. That architecture is quite feasible.